Welcome everyone to 8.1 arc length. Now this is the only section that we cover here in chapter 8. And it's nice, arc length actually will come up several more times during this course, not to give too many spoilers, but later on when we do parametric curves and when we do polar curves, we will also calculate out arc length. So it's an important subject. We only have one really section objectives, and that's to understand the formula and of course to use it and stuff. But we're going to go above just, hey, here's the formula. We're actually going to show why the formula is the way it is. So let's get to it with the first theorem. All right, the theorem is for the arc length formula, and the main condition is that our derivative needs to be continuous. So f prime is continuous on our interval a to b, then the length of the curve y equals f of x from a to b is given by L equals, and now we have a definite integral from a to b of the square root of 1 plus the derivative squared dx. Now, on the other hand, if your equation is given as a function of y, right, x is a function of y for some range between c and d, and g prime of y is continuous, then we can kind of interchange these roles of x and y, and we would get that the arc length would be the definite integral, then now from c to d of the square root of 1 plus the derivative, now g prime of y squared, all under the square root dy. Okay, so let's assume that this is the correct formula. We will explain later why that is the case, but let's use this to figure out what is the arc length of this function, x cubed over 12 plus 1 over x in the interval from 1 to 4. So, according to the formula above, I need the definite integral from 1 to 4 of the square root of 1 plus the derivative squared dx. Okay, so what is the derivative? So that's probably the first step, is to calculate out the derivative. Well, the 3 comes down and I would get x squared over 4, then minus 1 over x squared, right, because this is technically the power rule with negative 1. And now let's go ahead. Actually, before I plug this in, let's simplify. Let me get a common denominator. So this first fraction, it looks like I need an x squared on top and on bottom. So it'll give me x fourth. And then the second fraction, I would need a 4 on top and on bottom. Okay. So now we will plug this in. You'll see this will make our life a little bit easier when we go to square and simplify and whatnot. Okay, so now we need to square this and try to actually evaluate this integral. So let me leave this 1 alone for the time being. And now the denominator is easy, but the numerator I have to actually FOIL out. So when I FOIL this all out, I get my x to the 8th minus 8x to the 4th plus 16 divided by 16x to the 4th. Now let me actually cheat here. Instead of 1, let me get a common denominator. That 1's going to be the same thing as 16x to the 4th divided by 16x to the 4th. And now we can see that actually, well, we can make the 16x to the 4th and negative 8x to the 4th kind of cancel a little bit, and I'll get plus 8x to the 4th. So plus 8x to the 4th. There we go. And now, looking at this for a little while, we may realize that, hey, this is a perfect square, right? That numerator is actually a perfect square. The denominator we can simplify a little bit, get it out of the square root. And now the numerator, we can write this actually as x to the 4th plus 4 quantity squared. Check it by FOILing it all out. It's true. And now the square and the square root can actually cancel, right? And technically it would be the absolute value, but these are all positive values, right? As x to the 4th ranges from 1 to 4. So again, it's technically the absolute value of x to the 4th plus 4, but we don't really need that absolute value because they're all positive already. Okay, now techniques of integration, right? How do I integrate this thing? Well, this is a rational function. We should go ahead and kind of divide through. Luckily, we don't need long division here because it's just this 4x squared. And now I can evaluate this integral. and I need to evaluate it from 1 to 4. Okay, so when I stick in 4 into x cubed, I would get 64 over 12. If I stuck in 1 into x cubed, I'd get this 1 over 12 minus, and if I stuck 4 in, I'd get 1/4, and if I stuck 1 in, I'd get 1. So this looks like what, 63 twelfths, and then let's see, this is going to be minus negative 3/4. So let's go ahead and multiply 3 on top and bottom. So this is going to be 72 twelfths. So that's the same thing as 6. So that's a pretty nice answer right there. And you may realize, right, when we took the antiderivative here, that it actually looks pretty similar to the answer up here, and that's a coincidence, or the function that we started with up here. So again, that's a coincidence. That won't always be the case, so don't assume that you can just make that plus and minus and everything will work out. It probably won't. Okay, so let's talk a little bit of the idea behind why this formula works. And so I've sketched the same curve, it looks like 5 times here, and I want to go over an idea. So the idea is finding the distance between 2 points. So this right here would be a pretty bad estimate for the length of this curve, but it's a start, right? It's an estimate. We could add a second interval, right? So then I could take these 2 distances and add them together. And this would be a little bit better. But maybe if we took 4 straight lines, 1, 2, 3, 4, you can see it's getting actually a little bit better. So if I was to take all those distances and add them together, what about if we took 8? So here's quite a few of them. 1, 2, 3, 4, 5, 6, 7, 8. You can see that this is looking even better yet. And so in general, here's one with 20 line segments. If we were to add up all of these distances, it looks like it actually is approximating the curve quite well. There's only a few spots here where you can see it doesn't exactly line up, but otherwise it looks really nice. So then, what is the distance between 2 of these points? Well, let me give these points some coordinates then. Okay, so I'm going to just take 2 of these points kind of arbitrarily, and let me go ahead, get a thinner pencil here. So I'm going to call this one x1, and then the corresponding height will be f of x1. And this one will be x2, and the corresponding height will be f of x2. And I want to figure out what is this distance right here. And then if I could figure out that distance, I could add up, kind of all of the distances. So when we add things up, this will be an integral. Okay, so let's think about it here for a second. Let me get a bit thicker of a pen. Distance. Distance is supposed to be the square root. We think about this whole kind of Pythagorean theorem sort of deal, right? So the difference of distance will be x2 minus x1, and then the y distance will be f of x2 minus f of x1. Oops, looks like I didn't leave myself enough room here. Let me cheat a little bit. So yes, f of x2 minus f of x1. So that's the difference in the heights. Okay, well, another way we could write this is that this difference of x values is delta x, and the difference of y values is delta y. Still have to square this. Now imagine what would happen if we factored out a delta x squared from all of this. Well, for my first term, I'd be left with just 1. But for my second term, well, it doesn't really have a delta x. So really, it would appear a delta x squared in the denominator. When I take the square root of delta x squared, it's going to be delta x. But now let's let delta x get very, very small, right? So this is going to approach dx. And then this, I'm going to have 1 plus dy dx quantity squared. And that's another way to say the derivative, right? Okay, so now this is just for one line segment here. What if we had lots and lots of these? In this case, we only have 20, but you can imagine if we had 100 or 1,000,000 or something like this, and we range from a to b, and we want to add them all up, well, then we would take the integral from a to b of this thing. Let me go ahead and rearrange this so that dx comes at the end, as we usually like it to. But now you can see this is 1 plus the derivative squared, all under the square root, dx. All right, and there we have it. So now we have the arc length formula. We understand why the formula is the way it is. And next time when we come back, we'll finish up with a few more definitions and examples. I'll see you shortly.